header. It's something this component provides integrity and authentication for the data, ensuring the packet hasn't been changed. It's able to verify the sender's identity. And AH, this kind of mechanism does not provide encryption, so it's useful for scenarios where data confidentiality isn't good. So just concentrate on it. In our physical world, we don't need to protect the confidentiality of confidential data. For example, the news published by the government. The news published by the government should be available to the general public. And the government wish that the message can be received by the general public as well as the content cannot be changed. Of course, it wish anyone can see. So it means that there's no need to have the confidentiality protection. And the second protection is called ESP, encapsulating security payload. ESP provides the encryption for data confidentiality and along with the optional, but the default solution is integrity. And ESP is typically used for scenarios that require secure private communications, as it protects both the payload and also. So for simplicity, for you, any subject, you can just understand that ESP has confidentiality and it has information. Just make sense. You don't need to follow student and church. So we have transport terminal, or we can have the AH or ESP. So there's two. These are not two. So we can do some combinations. So we will have different jobs. And for example, this is the first one. The top one is the top one. This is the original package. And for transport. For transport means that we don't need to change the IP header. This one doesn't need to change IP. But after running this kind of IPsec protocol, we need to add some new header, right? And that new header will be inserted between the IP header and the payload. Between the IP header. But for the tunnel means that a new IP header will be created. A new IP header will be created, followed by the header for the IP set. So we will have this IP address and this IP address, and two IP address inside.
This is like it.
And this is for the AH purpose. Now for ESP purpose, the ESP purpose is that if on the transport mode that's the same, we don't change the IP headers, but we add some kind of header. But this kind of ESP is being weird and quite different from other security protocols because we have some kind of field in the field. Somehow different from the header. We have some separate fields in different locations. And also in the tunnel mode, we have a new. And that's one and two. It's a bit complicated, okay, because there's no consistency. If I was the designer, maybe I will just, for simplicity, maybe I will put all three blocks into one header to make it simple. But unfortunately, it wasn't invented by me. And I believe that the main purpose is to simplify the cryptography operations, because which part will be encrypted, which part will be authenticated. It's easier to mark, because for example, the last part has doesn't need to have any cryptographic credentials. Okay, this is the two the communication mode and also the protection way. And then to make sure that we can run this kind of IPsec protocol, there are two main components in IPsec. The first one is that we need to make sure that any devices can somehow generate a shared secret key. Because it's security protocol, right? We need to make sure that they can generate a shared secret key. And how to generate the shared secret key? That mechanism or that sub-protocol is called IKE. It's called IKE. It's a protocol for establishing security association and also managing keys. It's some kinds of automated the process of negotiating and setting up the setting one, which include choosing encryption method, blah blah blah, between keys. So if you can just understood the main task, you can just understand that the main task is to generate shared and for the IPsec protocol, it's different from other protocol. It has something called security association. This is a bit weird. And at the beginning, when you try to understand it, it looks a bit weird, okay? Because our protocol doesn't have this kind of agent or security association. This is a set of policies and keys established between two IPsec endpoints to define how traffic will be handled, and each SA is directional and handling the specific security protocols. We will define what kinds of protections, like SDH, ESP, and the keys to be used for network. I will further introduce this component, but here just highlight that. But before I go to that, I also need to this was the background. This was the background. I need to go back to introduce the previous communication mode and security protection. because we have transport mode, tunnel mode, we have the AX protection and ESP protection. Generally speaking, we should have four different combination results. But for simplicity, I just introduced two of them. Means that AH plus transport or ESP plus tunnel. I just introduced two to make it easier. And now, yes, we'll just have a look at this tunnel. The first row, that picture showing the original IP package. After running AH plus transport, the IP package will become like this, right? And this is the new header. Inside this new header, it will have 1, 2, 3, 4, 5, 6 fields. See, you can see that. Again, it also have the length. So length is everywhere in most protocols headers. And the detail is that, okay, that's the first field. Next, headers indicates the types of payload protocol following the pH. It points to the protocol type. Just to tell the traffic inside that field. Yes, and the middle lens is all have the lens. And also have the reserve. This is for future purpose. So yes, you can see that at the beginning. That's nothing new. Just for future purpose. And there's something important called security parameter index. This is unique identifier, okay, that point to the security association being used. It helps the receiving party know which SA and received key to be used for authentication. So how to understand this one? Okay, maybe I can explain this one. Suppose I'm Alice A and A, and communicate with both B. So it means that A and B are running the IP sample. But I will highlight that when B is talking to me, when Bob is talking to me, at the same time, Bob could be talking to another person, okay? And they are also running the IP sample. They are also running the IP sample. And SA, the role of SA is that each SA will manage or help through end-to-end communications. So it means that what? It means what? It means that inside both devices, there could have two SA. There could have two SA. One SA is somehow trying to manage the communications between Bob and Alex. And there could another SA trying to manage the communication between Bob and the server or the server. And that's why there are multiple SA on one devices. So this SA is to tell Bob which SA should be called or should be used to handle this connection. That's why it's called, it helps the receiving party knowing which SA and related key should be used for authentication. And also it has the so-called sequence number, and it's a counter that increase with each transmitted package. They provide replay protections by ensuring that all package cannot be sent. Because it's what is critical. This kind of sequence number is to make sure that once we reach one sequence, even the attacker try to replay or resend some kind of old package, that kind of package will be removed from this cloud. And just because of now the sequence is already only 100, but now there's a newly coming package showing sequence number equal to 2. It means that this must be something old, so it doesn't need to do any response to that old package. And the purpose is for integrity. It's for integrity. And the last one is the authentication data. And this field is used for carrier. It is used by the receiver to verify the authenticity of the data. It means that, for example, the signature is with isomorphic signatures, or the message authentication code will be put here. Will be put here for the verification. Okay, and this is how it looks like in AH plus the transform. Now, we look at how the ESP plus the timing look like. And so in the ESP plus panel, we have the original IP head plus the payload, right? And this part, this will not be changed, but we will add some header that transmit IP header and some kind of information related to IP security inside the IPsec ESP header and some kind of trigger of data. And inside this header, you will have two fields, SPI, sequence number, and this one will also have another file. Package names, and also the next header. And this result showing why somehow this design is because the yellow part they will be encrypted instead, and it cannot be seen. This we treat it as some kind of payload, and it will be encrypted, and this will be has some kind of authentication protection, and this is what it looks like. And so the next is also the details of each field, the function of each field. Again, that's because the same SPI, yes, to identify the SA used for this package. That's the same as the previous one. And the sequence number, this is also the same to make sure that there is no insult. To make sure that it's secure against the replay attack. And padding, well, padding is not hard security, but for communication purpose, to make sure that it's somehow consistent or align the data to the multiple of the decryption algorithm block size. Because the block size will need to have the top padding, right? That's something that we have to put inside. And the next header is to indicate the type of protocol inside the payload. Make sure that the receiver knows how to handle or which protocol should be run to understand payload. And also the authentication data will be covered or will be used to protect or information inside each field. But it's something called immutable. Immutable means that the data, only those data will not be changed when this kind of IP package was transferred from one devices to another devices. For example, like so previously I have introduced that in IP header there's an information called time of life, and that kind of the number will be decreased one by one after each hop. That number will be changed. If that, because that number has been changed, we cannot protect its integrity. That's why it's something called immutable. Means that only those data will not be changed during the transmission should be protected. Like that number, like the time of life, that will definitely cannot be protected. Okay, and this is the fields inside the IPsec protocol. Now let's look at the two components, SA and also the IKE. SA looks more like a mechanism. IPsec is a follow a policy-based approach to enforce the local security decisions of a system. On input, the requirements of settings, configurations from the administrators. It generates IPsec policies for which traffic require IPsec protection. For it's based on the IPGens or program. Which IPsec mode should be used is for transport of tunnel into input into settings. And we use the EAH or ESP for authentication of automation. And essentially, policy are like the filter and action points. I will explain what's the meaning of filter and action in the next picture. Then decide which package should trigger IPsec and what types of IP protection is required for those tasks. So field and actions. Okay, and to help you understand this one, I draw these pictures. And in these subjects, there are some pictures I took it from the internet. Of course, for some pictures I draw by myself. This is one of the pictures I draw myself. So there, suppose we have an IP package. Okay, I'm going to see the IP package. This is the IP policy, IPsec policy. The IPsec policy will have three main decisions. First is discard. Discard means that when this kind of IP packet is to be sent out or to be received, right? Before it handed to the up layer or to the bottom layer, it will discard this kind of or block the traffic. That doesn't mean the policy. Means that if this kind of IP packet is to be sent out, right? And then this IP policy will be delete this traffic. Of course, if it's sometimes receive IP package, the policy will just indicate without sending out, without sending it to the up layer. And the third one, bypass, is allow the traffic to pass without IPsec protection. Okay. It means that Okay, it means some IP package will be bypassed without any protection. For example, if this is something will be sent out, right? Send it out, then the policy will just ignore the protection and just let it go to the next layer and it will be sent it out. The most important related to IPsec protocol is that this package should be protected. Then that this will decided by the IPsec policy. So we will go to the protection parts. On the protection parts, right? And then the SA will do something. For example, we do the cryptography operations using encryption, authentications, integrity checks, as specified by the SA, inside SA. After the input, we will go to the next stage. Again, this kind of feature is for receive IP package or for IP package to be sent out. In the previous 2 years, I tried to create some questions. I found that the questions here not easy, okay? Not easy for understanding. Okay. You need to, it's better if you can listen carefully to this kind of questions, okay, based on these features. Suppose that A and B are running IPsec protocol. Okay. A and B are running IPsec protocol. It's not about Alice, okay? It's just device A and device B. Device A and device B are running IPsec protocol. For this kind of ESP purpose, for encryption purpose. Now, there's a student, Alice, from the CSCI 368. This student, Alice, claimed that all traffic sent out from device B cannot be eavesdropped by it. Let me repeat the question. There's a student, Alice. She claims that all IP package or data sending out from the device B cannot be eavesdropped by it. So the question is that, do you think Alice's claim is correct or incorrect? And then justify your answers. That's what kinds of questions could appear in assignment and also in exam. Can you understand these kinds of questions? That's fine. If you have interest, we can have some kind of email. But the answer is that no. Okay, it's no. For the anniversary could still be able to eavesdrop some data sending out from device B. Just because what? Because of this kind of features. The IPsec protocol running on device B is working in this way. It doesn't protect all IP package. Some IP package will go by bypass. It means that for those IP packets go to the bypass, it will not be protected by the IPsec protocol. So this one means that the approach can still be able to drop those IP package sent from this pass. You cannot claim yes. The algorithm cannot eavesdrop anything. That's the joke answer. You will get zero. Okay, and this is the SA. And so that's more than here. SA in IPsec is a set of parameters or keys, some kind of parameter that will be used for cryptographic operations that defines how traffic will be secure for a specific data flow, both for outgoing and also for incoming traffic under the protection procedure for security purposes. And the component inside this has an SPI. That's with each SA we have a name or we have a unique identifier because there could have multiple SA running on one device. We have distinguished it about not for SA. And this SA will also specify the cryptography algorithms for encryption, for authentication. Okay. It also contains the keys. Symmetric keys for encryption and authentication. And what's the keys? And that key is generated from another protocol called IKE. And for each SA, the network also have the so-called lifetime. This will determine how long the SA remains. That is, before the key or the negotiate. Means that, okay, suppose this set into 1 hour. It means that after 1 hour, this kind of SA need to be updated. They need to renegotiate the algorithms, and also they need to have an update keys. And that's the meaning of that. So where's the SA? This is the policy and also the SA, right? But then where's the IKE? IKE will generate a key for SA, right? And the IKE is not here. IKE can be treated as another component. After they generate the keys, they will pass the key to SA. Or they will treat it as, or SA will ask IKE for help when SA try to run the key negotiations. So now I have introduced with SA, right? And also what is the policy. Now we will go to the IKE. We will go to the IKE. IKE will be the last part that we should learn from this subject. And IKE protocol is responsible for establishing and negotiating time transfers between two endpoints, including selecting cryptography algorithms, generating shared keys, and setting values. So how to understand this one? Let's go back to this question. If we treat SA is a protocol, okay, and the protocol need to have some kind of algorithm for security or for need some algorithm for security cryptography purpose. Now, to be able to obtain the key and algorithms, they will call IKE as a subprotocol for help. They will call IKE as a subprotocol for help to complete running the SA. And the function of this subprotocol IKE is to negotiate. It's to negotiate the parameters, including selecting the algorithms, generating keys, and setting up these kinds of So that's the purpose of having IKE. And this IKE also have two. It was designed to have two phases. In the first phase, it's called secure channel. They would like to create a secure channel. The IKE first established a secure communication channel between two endpoints by authenticating them and setting up an initial secure channel for IKE itself. This phase ensures that both sides are legitimate and agree on the basic security. So they will just create a secure channel. Okay? It's not about the protection on IP package. So the first phase is just nothing about the IP. It's not about the IP package protection. No. It's just to make sure that they can have a secure channel. That's the main purpose. And after the first phase, the second phase of negotiation is that they will negotiate the areas for IP package protection. With the help of this secure channel, they will negotiate the IPsec-SAs for actual data protection. And during this phase, the IPA will define public parameters and keys, and also use by IPsec to secure protection. So it means that the whole protocol has been divided into two phases. Phase one. The principle is somehow like the network layers because it's not complex. So we make it easier and split into two phases. And each phase will focus on one. Will focus on one purpose. And that's the high level. And of course, the most complicated one is the first phase. Just because creating a secure channel need the public key cryptography, need the help of the public key cryptography. The second phase is much simpler. I think this is the same as the secure shell protocol. After the secure connection has been created, it's easy to complete the usual authentication. And the phase one, this is something I have to do. IKE first established a secure communication channel between the two endpoints by authenticating them and setting up an initial secure channel. This phase ensures that both sides are legitimate and agree on the basic concept and how to do it. And also, there are two options. Sometimes we have no choice. We have no choice of make it easier. We cannot make it easier because there are more money control. Here, there are two different approaches or two types of establishment. Phase one and two different modes. The first one is called aggressive mode. It's something about it has the mutual authentication and instruction is established in string messages or string interactions. And also have the called main mode. We use 6 interactions, 6 moves, 6 interactions, and have some kind of additional functionalities like anonymity from the user. Means that it has better protections compared to the aggressive mode. But everything has a trade-off because this takes 6 interactions and the aggressive just take 3 interactions. Now, again, we go to the cryptography part. Sometimes we do scores because this is about the key establishment or about the negotiations. Again, this example just shows that the most complicated part of security protocol is how to generate a shared security. That's the most complicated part. How to generate a shared security between any two entities. If we just assume that we have a shared security, well, that's much easier. That's much easier. Okay, that's the main mode, right? The main mode has 6 measures, 1, 2, 3, 4, 6, or 6 interactions. And the aggressive mode just have 3 interactions or 3 moves. But there are some kinds of advantage and disadvantage. This one is less efficient. This is more efficient. But in this kind of protocol, that message A denotes the identity A, and B denotes the identity B, denotes the identity B. And in this kind of protocol, A and B are somehow in public, sending without any protection. So it means that if the adversary is able to drop the communications, the adversary can see who are communicating with another. And we can see that this kind of protocol is, it doesn't use features port. The only solution is using the Diffie-Hellman key change. One party send the G to power X, one generates the G to power Y, also have the other elements. And this picture is somehow similar, sending G to X, G to Y. The main difference is, I think it's here. So we can see there are some kind of limitations. CKY is the cookie, that's not important for you to understand. But we have KM. KM maybe you can just understand it as a key master. It's somehow calculate from the nouns and the G to power X. This is the result of the change. And KE is computed from the KM. KE. So it means that only two entities, A and B, knows the KE. And they will use the KE that generates the KE to encrypt the identity A and B. Using KE. This is some kind of encryption. This therefore is some kind of encryption equivalent to ENCKE with the message. So you will encrypt the identity A and the signature of some values with the secret key, the signature A. And the sign one and the sign value is the hash value or the message authentication code, and it's just the input or aggregation. But the most different is that A and B, the identity has been encrypted. So given that if the adversary is doing this jobbing, the adversary cannot see who are communicating with who. And that's the main difference. And we have the GX, GY, and the signatures of the GX and GY and GY. And this is just a standard Diffie-Hellman key agreement, Diffie-Hellman key change of the second version to secure the key establishment. So yeah, that's this is the main difference of how the two protocol works inside this main mode and rest mode. So far we have learned so many applications of this one. For example, in the secure share protocol. Secure share protocol also have a Diffie-Hellman key change. That's the first one we have. And then next is in the TLS protocol. In the TLS protocol, we also have in the TLS protocol, we can have the key transport and also have the key transport and also have the key agreement or key change. But here in this one, it doesn't have the key transport. It's just only based on the Diffie-Hellman key change. Okay, just have the Diffie-Hellman key change past the signature. And that's why the reason I said that the Diffie-Hellman key agreement, well, it's a bit complicated, but I have to introduce just because it's the only solution we adopted by many security developers. And this one, SKA, and SKA is a signature by A using a public key. Okay, using a public key. But the public key, but the key pair public key, SKA was no different. And how to achieve this kind of public key and also the application? Well, it depends on the mechanism of the application. For example, we can also use the certificate. We can use the certificate to achieve this kind of verify that yeah, this public key indeed belongs to A, or this public key belongs to B. We can use the certificate. However, we can make it simple. It means that in the real world, if I'm the company, I'm one more company, I have to implement this IPsec protocol. I will not adopt the public key. I will not adopt this kind of digital certificate because we can use some kind of symmetric key to replace this one. That's why IPsec also support the use of reshared keys. They use the reshared keys. And this kind of reshared key means that two parties, A and B, they already have a so-called, they already have a shared security. They already have shared security before running this IPsec code. And they will input this kind of shared key. And this shared key will be used for authentication purpose during this kind of process to replace the signature. It means that there's no more public key signature of MAB or signature of MAB. They will be generate using a secret or share secret key to generate or replace this message. It means that they will use a message authentication code to replace the signature to achieve the same functionality, and to avoid the use of digital certificates. Maybe some of you could be curious. Okay, if they already have a shared secret key, what do we need to have running this kind of protocol to create another shared secret? They can use the shared secret key. They can just use this kind of shared secret key to have the so-called secure communication. They can just skip this kind of IKE process without the need of running or generating. Well, it's true, but I would like to highlight that the purpose of having this kind of IKE protocol is that the final secret key is somehow related to G to X, Y. It's related to GX. It means what? It means that the final key for communication will be fresh. Fresh means that from today, inside the IPsec protocol, the key will be different from the IPsec protocol to make the key fresh and make the key different, to make sure that even the key on the first day was stolen, it will not impact the security of IPsec protocol. But if Alice and Bob try to use the pre-shared key all the day for this kind of IPsec protocol, it means what? Once this kind of certain key in use has been stolen, that it will impact all communications every day. And that's the purpose of why we like to run this kind of IPE protocol. And this kind of security concept is called forward security. Okay, forward security to improve the kind of security. Well, it's a bit complicated just because we have many considerations. Okay, and about the last page. And as what I said, the second phase is much easier. Just because they already have a secure channel, they already have a shared key, and then what they need to do is just to negotiate the algorithms for real data protection. So I just use the switch message. So one party A will present a proposal and nonce an option you have to choose. And the recipient will confirm the proposal, nonce an option. And then they will run the confirmation of what they have negotiated. And the proposal is just to propose which symmetry algorithm will be used to encrypt data, and which algorithm will be used for integrity purpose. That's it. And of course, they also have something called optional deployment. This is called optional just because there are two option solutions. Because they already have a secure channel, right? Secure channel means that they already have a shared key. So they can try to renegotiate a key for data encryption. Or they can just use the previous key for data encryption. That's why it's called optional. You have two choices just to decide which key you want to use. And eventually it's the confirmation. Confirmation is just a hash. It's just a MAC of communication. So this is much easier. Just to confirm the algorithms, confirm cryptography evidence, and that's of course that's also one thing to learn. But it's this time is more important in this cryptography protocol, just to make sure that the IP protocol is running well. So yes, that's the IP protocol with two phases, and the most primitive phase is the phase lock. And okay, that's the end of the lecture today. See you on this Saturday.